Alrighty, in today's video, we're going to be talking about 7.2 exponential models. And basically, throughout the section, they just kind of show you different type of formulas you can use that are exponential, and then you just kind of figure out which formula you're going to need. A lot of times, they tell you what formula you're going to need, and then you take that and you plug in what you know, solve for what you don't know, and there's usually follow-up questions now that you've like found the constant variation, what happens after this year, and this year type thing. But your main ones are going to be like P of t equals P naught times A raised to the t, where this right here is your, if I can make an arrow, this is like your initial amount. This is your finished amount or final amount. This right here is time in years. Very specific on that years part. And this right here is your constant. 9 times out of 10, you'll be asked to calculate that, and they'll give you all the other stuff. And then once you solve it, then they'll ask you, all right, what's the final product when time is this? That's pretty much a lot of these type of questions that we're going to deal with. Another version of this exact same thing, you might see it as A of t equals A naught times A raised to the t. Again, this is still the final, this is still the initial, this is still the constant, and this is still time in years. Let's see. Another one that they might not typically give you is the compound interest formula. I've seen a lot of times that this is usually not given. And it's written as A sub t equals P times 1 plus R over N raised to the NT. This is still your final. This is like your initial, but this is more like what they call principal. The N is number of times in a year, and I'll explain that here in a second. This would be time in years. This is the same in, and then your R right here is your rate. And make sure it's a decimal because it's usually given to you as a percent. Now, what I mean by this right here, if it's yearly, yeah, so if it's yearly, I'll do it this way. It happens one time a year. If it's semi, it happens twice a year. If it's quarterly, it happens 4 times a year. If it's monthly, it happens 12 times a year. And if it's daily, it happens 365 days a year. We don't accommodate leap year. Now, if it's continuous, that's where this next formula will come into play. So if it's continuous, meaning it's constantly going every second, every hour. So if it's continuous compounding, the formula for that is A sub t equals P times E raised to the RT. This is still going to be time. This is still rate. And this is still going to be principal. And this is still going to be your final amount. The closer to 365 you get, the closer to continuous you get as well. There is a definition for E. Oh, I did forget one right here. If it's weekly, it's going to be 52 times. They do have one for hourly. I haven't really seen that one much, but hourly, that would be 8,760 hours in a year. And again, the further you go down here, the closer and closer to continuous you get. Again, they have a formula for E, but you don't have to know what E is, other than if you want to round about. E is about 2.718. But usually, if you just press E in your calculator, it does all that for you. You don't really need to know where E comes from, particularly in this class. But if you ever get to take calculus, there is a great limit formula or question that I usually teach when I do it to show you how E actually came about. But that'll be a question for that day, or if you ever take calculus. Um, and then they do give you one more. It's called the logistic curve. And it's f of x equals c over 1 plus a times e to the negative bx. A lot of different constants here. And I'll kind of explain them as I go when I do the problem. But A, B, and C are all different kind of constants. They don't actually quite represent things until you actually start graphing it. Then you'll realize what they kind of represent. And then, of course, E and X. E is a number and X is that variable of unknown. But that's kind of basically that's how the whole section is. It's just different formulas and tells you when you should use them. So let's look at homework type of questions. So we'll be on page 470 today. And we're going to look at question 7 to start. First question says the half-life of radium is approximately 1,600 years. So half-life is 1,600 years. Part A says determine A so that A sub t equals A naught times A raised to the t. Describe the amount of radium left after t years, where A naught is the amount of time t equals 0. So that's all the kind of information they give, and they expect you to solve for A. What you have to realize here to kind of solve for this is they give you more information than you think. If you're dealing with half-life, if you start with a number, let's call it 1, half of that will be left. You don't know your A, but half of it will be left in 1,600 years. So that means you would have half. Right? So even though they only said half-life equals 1,600 years and said solve for A given this, they actually gave you everything you needed in just this statement alone. And you could plug any number you want here. If you wanted to plug in 10, then the answer here would be 5. But regardless of what you do, you'll end up with that result of 1/2. Because reality right here, I don't necessarily need my 1, so I can break this down like this. And now I'm ready to calculate this. Now, I can do this by hand. I just don't know if I have taught y'all or what's the approach here. Okay. So the approach here, you would still need a calculator because there's no way I would expect you to be able to do this. There's a different approach we can do, but for now, we'll do it the way the book is doing it because later on you'll learn the other stuff, but you have to know the other stuff to be able to apply it. All right, so what we're going to do here is we're going to raise each side by 1 over 1,600. And when you do that, a power to a power, you would multiply. So this becomes 1600 over 1600. So they actually cancel and you get A equals whatever this is. So let's go and practice that real quick. Now I just need a screen share. Well, maybe I won't be able to get to show you. Looks like my calculator might be down. Yeah, I'm unsure what's going on, but my programs are not up and running anymore. I'll try to play with that in a little bit. Let's see. Well, I mean, you would plug this into the calculator. And I wonder if our little four function calculator can at least do it for us. Is there a scientific version of this? What is this button? Ah, okay, cool. All right, so I can. Clear. Can y'all see this? Oop. Well, it was there. Let's try that again. All right, and then I come back over here. And y'all don't get to see the calculator. That's what I needed y'all to see. Well, regardless, whatever calculator you have, you would just plug this in. So I'm going to do 0.5 to represent a half, and then I'm going to hit a exponent button, and I'm going to use parentheses so I can see that it will do 1 over 1600 for me. All right, what question we're originally on? Number 7. Half-life randomly approximately 1600. Amount left after 1600 years is half of it, whatever that half might be. Don't think it calculated it correctly. Something that big should be really close to 1. I got 0.000625. Let's see what's 1 divided by 1600. Oh, clear. 1 divided by 1600. Oh, I forgot to hit enter. Ah, all right, hold on. 0.5 raised to the 1 divided by 1600. Close parentheses. Enter. There we go. Remember to hit enter. And I'm going to go to about, I don't know, 4 decimal places, but that's going to be 0.9996. All right, so that would be approximately what my A would be. And then part B, again, I told you this is kind of how they are, is how much of 1 gram sample of radium would remain after 100 years. So now you're looking for your ace of T, or actually you're looking for ace of 100. So now I have 1 gram times my A, which is 0.9996, raised to the 100. And then all I got to do now is just type that in the calculator. So what I'm going to do is I'm going to do, don't need the 1. So that's going to take this value that I just calculated, and I'm going to raise this value to 100. And I get, again, go to 4 decimal places, 0.9576. 0.9576. So after 100 years, this is how many grams I would still have. And then part C, again, very similar to this, is how much will be left after 1,000 years. Because remember, the goal is 1,600 years. I should have half. So this time, come on, calculator. There we go. So this time I'm going to take this value here. Am I able to hit enter? Oh, I can copy it. Okay, so I double click it and I can bring it back. So then from there, I'm going to raise this one. Okay. Okay, raise this one to 1,000. And I get 0.6485. 0.6485. So again, I should be getting closer and closer to that half of that value. All right, so a lot easier with a Inspire or a bigger calculator. Having to do with what I have. Don't know why my programs aren't working, but I'll definitely figure that out in the next video. All right, let's go to number 10 then. So now these type of questions says the population of a certain inner city area is estimated to be declining according to the model. So again, it gave us a model. It says 237,000 times E raised to the negative 0.018 T, where T is the number of years from the present. What does this model predict the population will be in 10 years? So all you have to do is literally replace 10 or T with 10. If anything, this section's more or less, can you type it in the calculator correctly? And it'd been really nice to show you how to do so. All right, so I'm actually going to pull up my Inspire on my phone, and then just kind of plug that in. And again, if you need some more extra stuff, I'll definitely show you some more videos of it. Alrighty, so according to my little calculator, I got 197,959.04. Can have part of a person. So we're just going to round. So I have approximately 197,959 people. So I can see that this population is declining. So after 10 years, I'd go from 237,000 to 197,959. All right, so let's look at another one. So let's look at number 11. 11 says, in an effort to control vegetation growth, 100 rabbits are released in an isolated area that is free of predators. After 1 year, it is estimated that the rabbit population has increased to 500. Assuming exponential population growth, what will the population be after another 6 months? So this is basically using this equation without telling you it is. So my initial amount would be 100. My final amount would be 500. And they said that that hit after 1 year. So I now need to calculate my A. This is kind of nice because A to the 1 power is just A. So I just got to divide by 100. And my A is equal to 5. And they said, if this stays the same, what would it be in 1.5 years? So now I got to go, all right, well, what is my 1.5? So this says 6 months later. So that's why I said earlier that T is in time, years. So 6 months would be half a year. So 1.5 years. If I start it with 100, and I now know my constant is 5 raised to the 1/2, I just got to plug that into the calculator. So I'm going to do that. And so I get 100 times 5 raised to the 1.5. That's a lot of rabbits. So I got 1,118 rabbits. There you go. Let's look at another one. Let's look at number 12. 12 says, assuming a current world population of 7.75 billion people, an annual growth rate of 1.9% per year, and a worst case scenario of exponential growth, what will be the world population be in 10 years and 50 years? So again, it's still using this situation. You just have to kind of go about it a little bit differently. So my A sub t would equal A sub 0. And then in here, instead of A, you would have your whole plus your rate raised to the time. So that's the little change there. So in this case, we don't know A sub t, but we do know we have 7.75 billion people to start. And you have an annual increase of 1.9 percent per year. So that would be, again, 1.9% would turn into 0.019 as a decimal. I can't just put 0.019 here. I need to do 1 plus that since this is growth. Had this been a decay, you would do 1 minus that amount. So in this case, that would be 1.019. Then your time here for part A would be 10 years. So now we go, all right, well, what is that in 10 years? So that's going to be 7.75 billion times 1.019 raised to the 10th. And it looks like I get 9.35 billion. So 9.35 billion. And then part B, same concept, but this time it wants 50 years. So this is now going to be 7.75 times 1.019 raised to the 50. And when I do that, I get 19.86 billion. So 19.86 billion. Wow, that's too many L's. Yep. All right, let's look at some more you might see. Let's look at number 13. 13 says Maria has $3,500 that she wants to invest in a simple savings account. So right there off the bat, you're either going to use compound interest or continuous compound interest for 2.5 years, at which time she plans to close out the account and use the money as a down payment on a car. She finds one local bank offering an annual interest rate of 2.75% compound monthly and another bank offering an annual interest rate of 2.7% compound daily. Which bank should she choose? So we're going to be using that compound one since compound interest, since it does not say continuous. Recall that equation is it A of t or P of t? Yeah. So this will be A of t equals P times 1 plus R over N raised to the NT. All right, so in this situation, her first one says that she has 35,000. So my principal is not 35,000, 3,500. Wants to invest savings for 2.5 years. So my time is 2.5 years. At which time the monthly interest for the first bank, so we'll call this first bank, the interest rate is 2.75%, which would be 0.0275. And it's compound monthly. So that'd be monthly, which would be 12 times. The second one is that she still has $3,500. We'll call it second bank. It's still going to be 2.5 years, but now the rate is now 2.7%, which is 0.027, but it's compound daily, which is 365. So now we're just going to take all that information and plug it in. So I get 3,500 times 1 plus 0.0275, divide that by 12, raise that to 12 times 2.5. And then on the flip side, I'll do the same thing here. This would be 3,500 times 1 plus 0.027 divided by 365, raised to the 365 times 2.5. So let's figure out which one brings more money. So for this one here, she would have $3,748.79. And then this one right here would be $3,744.40. So looking at it for about $4 more, she should go with the first bank. That's pretty much all you gotta do is plug it in and then just judge the numbers. All right, so look at number 15. Tom hopes to earn $1,000 in interest in 3 years' time from $10,000 that he has available to invest. To decide if it is feasible to do this by investing in a simple monthly compound savings account, he needs to determine the annual interest rate such an account would have to offer for him to meet his goal. And then what would the annual rate of interest have to be? Okay, so two-part question. So first part, Tom hopes to earn $1,000. So he wants to get a total interest of $1,000. So we'll call it interest is $1,000 in 3 years. So time would be 3 years from 10,000. So we get a principal of 10,000. So basically what this means then is if you add that to 10,000, we get 11,000, and that would be my total amount. Decides if it's feasible, he needs to know which one to invest, how much to invest, or how much the interest rate should be if he invests compound monthly. So I see that this is monthly, which is 12. All right. So what would the annual rate of interest have to be? So here we go. So I would plug in, again, here's my formula. I now know this amount. I want to have 11,000 at the end of it. I start it with 10,000. I don't know my rate. That's what I'm calculating. I know my N is 12 and my N is 12. And he wants to do this in 3 years. So here is my equation. So for starters, we'll divide this by 10,000. Okay, so 11,000 divided by 10,000. 1.1 equals 1 plus r to the 12th times, I'm going to go ahead and call that 36. The reason I'm going to do that, because now I'm going to raise both of these sides by 1 over 36. When I do that, I get 1.0027, because that right there will go away, equals 1 plus r over 12. I'll then subtract 1 from this. So minus 1. And that gives me 0.0027. And then the last thing I'm going to do is now multiply both sides by 12. And I get a grand total of 0.0318 equals R. So therefore, my final answer would be 3.18%. So if he wants to make $1,000 in 3 years off his 10,000, he needs to find a bank that's willing to do it for 12 months at 3.18% interest. So even though it's the same formula, we're just solving different things. And that's pretty much all these different type of problems do. All right, let's look at another one. 17, we get the function C of t equals C0 times 1 plus R of t. It goes, this model, the rise in the cost of product that has a cost of C0 today. So that's our initial amount. So even though it's a different formula, it's telling us it's the same thing as the rest of them. Subject to an average yearly inflation rate. So here's my rates. Here's my time. And it did say years once again. If the average annual rate of inflation over the next decade, so time is 10, that's what a decade is assumed to be 3%. So that's 3%. So that's going to be 0.03. What will the inflation adjusted cost of 100,000? So here's my initial amount, 100,000. House be in 10 years. It then restates for you that that's what it is, and then round your answer. So here's my initial. It wants to know what the final cost would be. So I get 100,000 times 1 plus 0.03 raised to the 10th. Looks like I get 134,391 and 64 cents. All right. And then let's see what else we got. Oh, so then there's questions like this one here, like number 23. It says Marshall invests $1,250 in a mutual fund, which boosts 5.7% annual return compound semi-annually. So here we go. So we have an investment. So here's my principal of $1,250 in a mutual fund, which boosts a 5.7%. So 5.7%, which is 0.057. Annual return compound semi-annually. So in semi would be 2, which then it also tells you twice a year. After 3.5 years, so time, 3.5 years, Marshall decides to withdraw his money. Hold on. All right, so part A then says how much is in his account. So let's just plug it in. So we get, again, we're looking for our total amount. We have 1250 times 1 plus our rate of 0.057 over our time, which is 3.5. Nope, I lied. It's R over N. Semi was 2, and then 2 times 3.5. All right, so let's see what that answer is. So we get 1250 parentheses 1 plus 0.057 2, raise that to the 2 parentheses 3.5, and it looks like it would be a grand total of $1,521.74. Part B then states how much has he made in interest from his investment. So in that case, you would just have to subtract 1250. I'm going to take all of this, and I'm going to subtract 1250 from it. And you would see that he ends up making a grand total of $271.74. And that's pretty much all you got to do on those type of problems. Let's look at another one. Let's look at number 24. 24 says Adam is working in a lab testing bacteria population. After starting out with a population of 375 bacteria, he observed the change in population and noticed that the population doubled every 27 minutes. All right, so here we go. So we have a grand total of 375. It doubled, so we just need to do 375 times 2. You get 750. Then the A would then be 2 because it's doubling, and it's doubling every 27 minutes. Oh, so you'd have to turn that into hours. So there is 60 minutes in 1 hour, and there's 24 hours, so there's 1440. So there'd be 27 over 1440. Again, this is all coming from the a sub t equals a sub 0 times a raised to the time in years. So this is my doubling factor. So then part A then says find the equation for the population P in terms of, find the equation for the population P in terms of time T. Oh, it did say it in minutes. It changed it. So we'll keep it in 27 minutes. And I think, I'm assuming it's doubling. I'm going to have to call this A and say this is 27 minutes. So find the equation for the population P in terms of time T in minutes, rounding A to the nearest thousandths. Yeah, I'm assuming it's doubled. That we know that this doubled in 27 minutes. All right, so then from there, I can divide this by 375. So that right there would equal 2a raised to the 27. So now we're going to raise that to the 1 over 27. So then my a would equal, let's see, 2 raised to the 1 divided by 27. And I get 1.026 and then a whole bunch of zeros and a whole bunch of numbers after that. So that's pretty good. So that's a thousands, right? 10 hundredths thousandths. So I got my A. So then part A, to write the formula out, it would then be A sub, I guess I said P. So this would be P sub T equals 375 times 1.026 raised to the 27. Or nope, it'd be time, just time T. I had to use 27 to calculate it, but this would be what the formula is. And then after that, part B, then ask, all right, well, find the population after 2 hours. Well, since this is in minutes, 2 hours would be 120 minutes. So then we just calculate that. So it's still relatively easy. It's just going to trick you up with changing its units. So do pay attention to that part. So then I get 8,160.46 bacteria, whatever the bacteria might be. Alrighty, let's look at number 31. Let's look at 31. 31 says depreciation in the decreased of an item's value can be determined using a formula similar to that for compound interest. So it gives it to us like this: V equals P times 1 minus R raised to the T, where V is the new value. If the particular car you buy upon graduation from college costs 17,500, so that's going to be my P, and depreciates at a rate of 16%, which is 0.16. Per year, what will the value of the car be in 5 years? And when car be in 5 years when you pay it off? All right, so then we just kind of plug it in. So this is going to be 17,500 times 1 minus 0.16 raised to the 5th. So this will be 17,500 parentheses 1 minus 0.16, close parentheses, raise that to the 5th. And it will be worth, after you pay it off, $7,318.71. So there's your resale value. All right, so I can't actually do number 34 and 36 the way I want it to do, but it is pretty much the same thing we did with linear and quadratics and all other different types. You would just plug in that table, and then when you go to regression lines, you would just choose exponential, and that's what you would write down for part A, and then you would use that to estimate whatever the question is. If you need me to show it, hopefully I can get the app to work. And I can add another video in for y'all. But other than that, that will be pretty much all that I'll show you in this video. And of course, as you need questions, keep emailing me. Other than that, that is all I got for you today. See you in the next one. Bye for now.